Okay, let's get started. So I hope you've had a chance to look at the control this week already. If you'll see it's not easy. It was a fair bit of work, but I wanted to. Well, I hope the first question is not too bad. You just have to use the rule for taking the covariant derivative, which we've seen in principle. We've seen it for the formula in class, and you just have to sort of plug in and apply it to the plug it in and apply the formula for the covariant derivative to the case of the metric tensor, and then you have these you have these terms involving the Christoffel symbols, but you can write the Christoffel symbol in terms of the metric, and so you can kind of imagine if you develop all those terms that you'll find that there's some cancellation. So, but please show your work and show where what those terms are that cancel. So I think that's in principle that should be straightforward. But it does take practice to work with those equations. As you've seen, we've had some practice with the geodesic equation, and it's not immediately obvious. You have to distinguish between the covariant, the dummy indices and the free indices and form the appropriate sums and etc. But I anticipate that at least conceptually that's not the challenging part. The challenging part was really asking you to do these calculations of time dilation, gravitational time dilation. And these are quite subtle, right? That we're getting into effects that confused communities of physicists for a long time. That I think it's been sorted out within the relativity community. People know how to do these things, but it was hard for them to learn historically, and it will not. So it's a bit challenging for you as well, and or that sort of history repeats itself in the classroom, right? Every year. In the sense that the things that the community struggled to learn originally, new generations of physicists have to struggle with that as well. So that's why I created this TD that I wanted to discuss with you today. Well, here it is. I think you can see this file here, and I was motivated by my example in another class. I teach English, and we've been watching these very nice videos by Kurzgesagt, which is a German word for in a nutshell, and they have one on colonizing Mars. But we're going to just, even the phrasing of this sentence might strike you as strange. Calculate the rate of difference of aging on Mars and on Earth. That might be misleading in the sense that, there's no advantage of sort of living on Earth and barring biological effects, there's no advantage in living on Earth in that you somehow age more slowly. It's more the but as we'll see in this calculation, if you put a clock on Mars, it's going to measure more time than happens here on Earth, and it's the same effect that it's analogous to the effect we saw in the class with the Italian Alps experiment, with the cesium atomic clocks on Plateau Rosa in the 3,500 meters, and the other one in Torino, 250 meters. And so, and this is to be understood from the perspective of a space-time curvature. But in doing the calculations, well, that's what we'll step through here step by step. But the key thing is to find the trajectory of the clocks, and then you use the line element, the ds squared, to calculate the interval of proper time measured by the clocks. Okay, so that's why I sorry, is there a question? So I'm going to assume that's not a question for me because I can't quite understand what you're saying. Okay. Yeah. So we imagine putting clocks on Mars and on Earth. I mentioned the type of clock. The point is that they're very accurate clocks to 1 part in 10 to the 12. And in the first calculation here, we're going to ignore, just to simply, the thing's complicated enough, we're going to ignore the gravitation of the planet and the rotation of the planets, and just concentrate on the gravitational field of the sun. And we'll see that is 10 times bigger than any effect due to the gravity of Earth or Mars. Not too surprising. I mean, the 99% of the mass of the solar system is in the sun. Jupiter, most of the other mass, by the way, is in Jupiter, which has more than twice the mass of all the other planets combined. So Mars and Earth are tiny little specks in the solar system. So we can concentrate on the gravitational. In a first calculation, we'll concentrate on the effect of the sun. And we're the only space-time we've studied besides Minkowski in any detail has been this Schwarzschild, but it's very useful. Schwarzschild applies when we have a spherically symmetric space-time that's static, so it's not changing in time. And for that to be the case, we'd have to have the sun perfectly homogeneous and spherical and not rotating. The sun is actually rotating, as you probably know. The sun rotates, and it's not so easy when it's a big ball of gas. So it's different parts of it are rotating at different rates. It's rotating at about one period every 25 to 30 days, depending on where you are. what part of the sun you're talking about. But we're gonna ignore that rotation, and and otherwise we'd have a more complicated space-time. But this is the dominant effect, is just the Schwarzschild type space-time. And the key point is how is really the distance from the Earth to the sun, and Mars to the sun. And so let's let's just take their semi-major axes as their distance of their orbit from the sun. So I needed indices to distinguish the Earth and Mars, so I'm using T for Terre and M for Mars here, and let's just pretend those are constants. In other words, circular orbits. And the nice thing about this calculation is our results are building on things we've learned earlier. So we in the last TD we did last Saturday, we derived this relationship. This should remind you of or at least you've seen something similar in Kepler's orbits, where this is the angular velocity of the orbit, actually no, sorry, you'd have to do some calculations to. You'd have to take the ratio of these this angular velocity and this rate of change of time here to have the rate of change of angle with respect to coordinate time here. You'd have to get rid of the proper time, but anyways, you can you can get to Kepler's approximation from this. So these derivatives here are the derivative with respect to proper time, and so we're going to, m is the mass of the sun, Newton's constant, and r is the radial coordinate in the Schwarzschild coordinate system. Okay, so the first thing to ask yourself is to make the connection between the orbits of the sun or the orbit of the planets about the sun and the geodesics. So why were we studying geodesics? Because those are the paths of free particles in a gravitational field. And so if you think of the planets going around their star, what are the forces on those planets? The only force is gravity in sort of Newtonian physics terms, but in relativistic gravity, we think of it not as a force but as space-time curvature. So in other words, there is no force. So these planets are following geodesics. So that means we can use this result from TD7 about the geodesics, the circular geodesics in Schwarzschild. And we're going to approximate the planets as being, essentially circular orbits. Now we want to know time intervals measured by clocks on, I suggested we think of it that way so that it's more concrete what we're talking about. So we're talking about, we place these cesium clocks on Mars and Earth, and we want to measure or to know that the time intervals that they measure. But clocks measure proper time. And they measure proper time along their trajectory. Their trajectory does not have to be a geodesic. It just has to be a well-defined curve along which we can measure this ds squared, or the proper time. And for instance, in the Italian clock experiments, those clocks are not following geodesics, right? They're just sitting there in with fixed spatial coordinates on the Earth, either in a lab in Torino or on top of a mountain in the Italian Alps. And as we saw in the last in the exercise, the control continuity you just did, that in the Schwarzschild spacetime, fixed spatial coordinates are not geodesics. So if we're sitting here stationary at the moment, we are not following geodesics. But that makes sense, right? Because we feel the effects of gravity. We're being pulled. What we feel is that we're being pulled down to the Earth. Anyways, back to this problem. These planets are moving along geodesics, and our clocks are following their geodesics. So we're looking for proper time intervals along geodesics, and so we can use this relationship between phi dot and t dot that for circular. So we're treating them as circular geodesics. Now, Mars is a massive object, so it follows a time-like geodesic. The other, as opposed to a space-like or a null geodesic. So in that case, ds in our sign convention, ds squared is greater than 0. And the physical interpretation is that it's the speed of light squared times the proper time interval along that geodesic. So there's the argument for why this clock or that this ds calculation is going to be the relevant thing, because it's going to give us, we have to take the square root, but it's going to give us, and divide by c squared, but that's going to give us the proper time interval along that trajectory, which happens to be a geodesic. So we use equation 1 is just ds squared for Schwarzschild with all 4 terms in it, and we see the coefficients only depend on theta and r here, and the rest are parameters. Of course, it depends on the mass of the sun and Newton's constant at the speed of light, etc. But in terms of variables, in terms of coordinates, it only depends, these terms in the ds squared, we call this the line element, it depends on r and theta. But we can choose our coordinate system so that theta is pi over 2, so sine squared becomes 1, and d theta will be 0. But we need to know r. So r we're going to set to be the distance from the center of the solar system to Mars. Let's start with the calculation for Mars. It'll be the same for Earth, except you change all the parameters to that of Earth. And I gave you these distances here. This is almost 50%. Later, I was thinking I should have just called this 1 angstrom and this 1.5, not angstrom, astronomical. Sorry, 1.5, 1 astronomical unit. By definition, our distance from Earth to the Sun is 1 astronomical unit, and Mars is about 1.5 astronomical units, and that would have been accurate enough for our calculations. I should have done that, but instead I looked it up in kilometers. And there's just one conceptual point here, that radial coordinates are not physical distances in a curved space-time, right? Because to get a physical distance, you have to integrate this ds, and because of these metric terms, in particular this one here, you don't, dr on its own is not an interval of distance. It's really dr times the square root of this metric term that would give you the physical distance. But the point is that this quantity here, giving a departure from 1 here in this metric term, for basically anywhere in the solar system, you could be at the center of the sun, the surface of the sun, anywhere within 1 part in a million. This is just approximately 1, because the space-time curve, same is true for this term here. And the reason is that the gravity of the sun is actually really weak in relativistic terms. So that's what I'm trying to say here. The radial coordinate r is equal to the distance to the center of the coordinate system, which we take at the center of the solar system, to a very good approximation. It's a good approximation because gravity is weak in the solar system. Of course, we have to be careful with these arguments because we're looking for changes in clock rates, but it would just basically put our clocks at a slightly different orbital distance to if we took that spatial curvature into account here. So that's not necessary. So let's just set the radial coordinate equal to the physical distance. So we want a ds squared, which will be c squared times the proper time interval measured by our clock on Mars. So we want ds for a trajectory which has a fixed theta. It has a fixed radial coordinate because it's essentially a circular orbit, but that leaves 2 coordinates that are changing, coordinate time and the azimuthal angle. But fortunately, we have a relationship between t and theta, or actually it's expressed between t dot and theta dot, which are the derivatives with respect to proper time here. So I'm going to write this theta term. There were probably several ways to do the algebra, but I thought to do it this way. We replace theta here, or d theta, with theta dot squared multiplied by d tau squared. The reason being, then I could absorb this term or move it onto this side of the equation, and it would or sorry, first I want to write, yeah, it worked even better here. So we use that equation 3 for the circular orbits of geodesics, wherever that is here. And then we need this phi dot squared. So we square this thing and it becomes t dot and time squared times this thing without the square root. And then then what did I do? Sorry, I did this a week ago and I haven't thought about it since. Sorry, I gotta think. Of course, yeah. So what is t dot? It's dt d tau, and then if you multiply that by d tau, you just get dt, and then the whole thing squared. That gives me a dt squared. So then I can combine this term with that term, and then I notice it's actually quite we have a common denominator here because r squared cancels this and becomes just 1 over r with a I can multiply on top and bottom by c squared, so I have a common denominator. And so instead of -2 here, I have -3. So this just adds to this term here. And then we take the divide by c squared and take the square root of both sides. And yeah, so this gives a nice relationship between the proper time of a clock on Mars in its circular orbit about or approximately circular orbit about the sun, for a given interval in Schwarzschild coordinate time. So that's what we've accomplished with this equation 5. And then, of course, the Earth is in a similar situation or the clock on Earth is in a similar situation as that in Mars, except the only thing that changed was that we have a different radial coordinate here. So I just rewrite the same equation, but with the radius of Earth, the Earth's approximately circular orbit. And now we were interested in comparing clocks on Mars and Earth. So I take the ratio of these two quantities. So I divide the left-hand sides here, and then I divide the right-hand sides. And the beautiful or the useful thing is that the interval in coordinate time cancels. And but I have to take the ratio of these two quantities here. The one with Earth having the minus sign because we divided by the interval for the Earth. And historically, there's been it might seem like I'm harping on about these points here, but historically, there's been a lot of confusion about these different time intervals and what they mean. And in fact, I've seen an article written about exactly this fact that this dt here is the coordinate time interval, and we want to compare the proper time measured by a clock on Mars. I'm pointing at Earth, but on Mars and Earth in the same coordinate time interval. why are we doing that? Well, because the coordinate time is a global coordinate system that applies throughout the solar system. And so we can use it to find the time measured by these different clocks at separate locations, but in the during the same time interval. And what do I mean by that time interval? I mean the same coordinate or global time interval. I guess it's awkward to find the language because the language we use is been developed before Einstein discovered relativity, right? So it's a little awkward to talk about it, but we basically have to distinguish between coordinate time and these proper times. And the useful thing about coordinate time is that it's part of a global coordinate system. Even that, so it's global for the Schwarzschild space-time. And this is, as I'm sort of alluding to here, this sort of thing has led to endless confusion in the relativity community, but it's, I think, been sorted out, after decades of people arguing about it. So the coordinate systems are useful because they give us sort of a global system for comparing things. Okay, now it's just a question of doing some algebra once we've done the math and the physics of interpreting these things. And so we know that these things are really, really small. Anywhere in the solar system, this would be 1,000,000 times smaller than that. And it's even smaller than that because we're a long ways away from the sun here. And so we can do a very good approximation, just bring this 1/2 down here and divide 3 by 2 and forget the power, and bring this minus 1/2 down and again divide by 3 by 2, but then change the minus to a plus here. So it'll be plus with the Earth and minus with Mars there, as I have here. And then we just multiply these out. And of course, this is the small term, so we ignore the small term squared. But we have one times 1 is our big term, and then we've got 2 sort of intermediate terms. This one times 1 and minus that one times 1. So we have the 1 over the Earth r minus 1 over the Mars's r, and we can actually bring it, factor out all these other constants here, everything except the radial coordinate. And so this, once you do the math, you get 5 times 10 to the minus 9. So this is much stronger than the gravitational time dilation that we found for the Italian Alps experiment. In fact, it's still extremely small. I had to make it come out in seconds. I had to use the a decade, 10 years, because it is still in milliseconds if I went per year. And yeah, so so that's the number. I thought it, well, I should pause there and ask you, does anyone have any questions about this? It might take a minute to sort of sink in what the physics of what we're doing. Well, if any questions come to you, don't hesitate to send me an email later. If they come in the next few minutes, just type in the chat here or start talking. I think I should be able to hear you. If I don't respond, it's because I don't hear you. So just type here in the chat for any questions. See if I have any observations. Yeah, I can't think of anything. Well, as I said, you know, as we saw in the Italian Alps experiment, there is gravitational time dilation even here on Earth. So we should think about that. And the Earth is also not a stationary thing. It's a spinning ball, and so is Mars. Mars spins actually at a rate only slightly slower than Earth. Its day is like 24 hours long, or 20, or no. I forget. I have it written down here somewhere, but it's very similar to Earth. But well, more importantly, the gravitational field is much weaker on Mars. So we should at least worry about that. And but we're going to find it's this gravitational time dilation by the sun is much big, or 10 times bigger than the clocks on Earth have been sort of, I hesitate to use this language, but they've been slowed down, or they've slowed down with, maybe the proper way to say it is they've slowed down with respect to the global coordinate time on Earth more than on Mars. That's the safest way to say it. Clocks don't slow down in the sense that they just measure time, right? They measure how much time is there, and the clocks that we are considering here are ideal in the sense that they don't slow down or speed up. They just measure the time correctly. But there are different amounts of time in the same amount of coordinate time, depending on where you are in the gravitational field. That's what this spatial curvature or space-time curvature is all about. Okay, so let's take that into account. So or at least the gravity, we're still going to ignore the rotation, but let's take gravity into account. Now, this is a little bit tricky. I had to be honest, I had to think about this one a little bit because we don't have a single space-time here. If we want, you know, we want to approximate Mars and Earth as their gravitational fields as being essentially Schwarzschild. But then there are different spacetimes, right? There's the Schwarzschild of Mars and there's the Schwarzschild of Earth, and they're different. But I think I came to terms with this by considering that they both have observers at infinity. And so we can measure the gravitational field with respect to, we can measure our rates of clocks at the surface of the Earth, for instance, compared to a clock at infinity. And similarly, we can do the same for Mars. And we can assume that the clocks that are at infinity, whether you're at infinity in Schwarzschild, in with Earth at the center, or with Mars at the center, where either way you're at infinity. So those clocks at infinity should agree with each other. So that's our sort of common reference point, will be clocks at infinity. Now I needed two things: the mass of the planets. Here's Earth's mass, and the mass of Mars. It's substantially less, right? It's almost 10 times less, even though its radius is a little bit more than half of that of Earth. But of course, the mass goes like the cube of the radius. So again, we're going to do simplifications of imagining that these planets are. This is the mean radius of the Earth, right? It has a 20 kilometers greater radius at the equator than at the pole, but we're ignoring effects like that, and because it's only 20 kilometers out of 6,371. So just treat it as a sphere. Same with Mars, but Mars is a smaller sphere. Okay, so a clock at the surface of the Earth. Again, now let's forget about the solar system for a minute and just say, let's focus on the clock at the surface of the Earth. It's not following a geodesic, but it's following a world line. That's it's a massive particle, so it has to follow a time-like world line, and therefore ds squared is greater than 1, and therefore this ds is equal to the proper time interval, with the speed of light just providing a conversion of units here. So we made that argument at the beginning of the last solution, and we're applying it again here. It's important because not every interval in spacetime is time-like. We have space-like intervals as well. We also have null or light-like intervals where ds is 0. Okay, so again, we go back to the Schwarzschild line element with all 4 terms in it. But now we have, just like in the TD exercise, in the last control exercise, we have the spatial coordinates fixed. So only the coordinate time enters into the ds. And I've gone ahead, because I only had 1 term, I went ahead and took the square root of this line interval, and I divided by the speed of light to get rid of the c here. And of course, let's use the mass of the Earth now. This is the standard symbol for mass of the Earth as opposed to the sun. This is also this circle with the dot is the standard symbol in astrophysics for the referring to the sun. So RT is the radius of the Earth. So we have this relationship between proper time by a clock on the surface of the Earth. This is and the coordinate time of a approximately Schwarzschild space-time around the Earth. So this is the same expression we used in the class when we were understanding and analyzing the Italian Alps cesium clock experiment. So we've ignored the fact that the Earth is rotating. Where did that approximation come in? Well, when we said that phi was constant here, phi is not the longitude on Earth, because we don't have a coordinate system that's rotating with Earth. We have a coordinate system that's not rotating with respect to the fixed stars, but Earth itself is rotating with respect to the fixed stars. So if I have a clock that's just sitting there on Earth, then its phi is spinning around at 1 revolution per day. We're going to talk much more about this when we solve the last exercise today, which explicitly takes this motion of due to the Earth's rotation into account. We don't take this is a little bit complicated to talk about, because the rotation of the Earth would actually change the gravitational field. So that's yet another rotational effect that would have to be taken into account, or, to have a 100% precise calculation, we'd have to take that into account as well. But that would involve using a more complicated space-time, which and also it would lead to an even smaller effect, and we're going to find even the motion of the clock itself is negligible. But this gravitational effect of the Earth is not quite negligible. It's 10 times smaller than the sun's gravity, but it's small. So we're going to neglect the rotation of the Earth, both for its gravitational effect on the gravitational field and the motion of the clock. And we'll justify this later. Now let's imagine we have a clock that's so this is we need to sort of comment, as I said earlier, we need to compare clocks in 2 different space times, one Schwarzschild around Mars and Schwarzschild around Earth, and so I need a common sort of reference point, and I so as I mentioned earlier, I'm going to use clocks at infinity. So in other words, let's consider a second clock in the same space-time around the Earth, but very far from the Earth. So let's just take R to tend towards infinity here. I can use the same formula. I just let R go to infinity here, but then this term goes to 0, and I just have 1 as the metric coefficient between the proper time and coordinate time. In other words, clocks at infinity measure a proper time equal to the coordinate time. So if you like, in the Schwarzschild space-time, you can say that if you want a physical interpretation of coordinate time in Schwarzschild, this result actually just gives it to you, doesn't it? It tells you that the physical meaning of this coordinate time is that it's the time interval. The coordinate time interval corresponds to a physical time interval measured by a clock, but it's a clock at infinity. Any other clocks are going to measure less proper time in that given time that a clock at infinity would measure. Okay. I'm just thinking about how obvious that is. I think that has not led to any controversy in the history of relativity. So I think that one's shouldn't bother you too much. That's by we give a name for this type of space-time where we have this result. By the way, this is called an asymptotically flat space-time. And I don't even know how to spell that actually, but I think you know what I mean, because it's a similar word in French. Uh, this approaches that in this limit, and but this is a flat space-time result. In fact, all the curvature effects go to zero or actually, yeah, as r goes to infinity. So in other words, this ds approaches that of Minkowski space as r goes to infinity. Okay, so this now I can take the ratio of my proper time measured by a clock at infinity and the clock at the surface of the Earth, and again the proper time or the coordinate time intervals cancel. It's the same coordinate time interval, and I just have in fact this term, and that term it was on the in the denominator, so I just put a minus sign here, and now I've done the hard work. I can just to do the same thing, replacing these parameters here for Earth, just replace them for the Mars parameters, and we'll have the corresponding relationship for Mars. And of course, what we want to do is compare we don't really care about clocks at infinity. We care about clocks on Earth and on Mars. And so we want to now take the ratio of these two and assume that these that d tau infinity is, whether it's infinity in around Mars or infinity around Earth, it's infinity's infinity. It's the Minkowski space sort of flat space-time measurement, and so we argue that those are the same, and they cancel. And if we divide, I guess this 13 by 14. Then we get this equation with with the positive. This became the positive one because we have this is the one that flipped, and now again to an even better approximation. Actually, these are less than 10 to the minus 6, and so these coefficients. I'm referring to this whole coefficient here. It's a dimensionless coefficient, and it's much smaller than 1. Because space-time curvature effects are small around the Earth, they're even smaller than around the Sun, and so I can just bring this minus 1/2 down here, and it'll get rid of the 2 and change that to a plus. And here I keep the minus sign, but I get rid of the 2, and now I have 1 plus a little number times 1 minus a little number. I'm going to ignore the little number squared, or little number times little number, and just have a 1 plus this one minus that one. And I'm going to factor out the g over c squared, but keep the mass over the radius, and mass over radius here. And the key thing is the radii are a little bit different, but the masses are hugely different. And so Earth wins out here, and we have a positive number here, which is coincidentally, it's a similar number, 5.5, but it's 10 to the minus 10 here for the difference, than what we got in the first calculation. It was 5 something times 10 to the minus 9. So it's what let's remember what this means. This is the rate of the time difference in clocks on Mars and Earth due to the sun's gravitational field here. And here in the second calculation, we're just looking at the respective gravitational fields of Earth and Mars, and finding a effect that's 10 times smaller, but working in the same sense, that we have more time on Mars for a given time interval on Earth. But yeah, so we'd have to go to in a 10-year time period. This corresponds to still less than a second, and so if I combine that with the earlier one, instead of 1.6, I get 1.7 or 1.8, I guess here. What was it? 1.68, I think. Or 1.61, or say 1.6, and together they give almost 1.8. So it's sort of a 10% effect. Finally, I want to convince you that rotation is really negligible. So this is a fairly simple calculation, but it's, again, like many things in relativity, it's a bit subtle to think it through carefully. So I set you up to think about this earlier, right? We said we're going to ignore the rotation of the Earth on the gravitational field of the Earth. That's an even higher order effect. But we're going to take into account the fact that our clock that's stationary on the Earth is actually spinning around, because the Earth is moving, and it's moving at a great rate. You can just quickly convince yourself of that. If you think, well, if I wanted to fly around the Earth in a day, I think that we have airplanes now that could do that, but they would have to be supersonic airplanes, and they would be they'd be going quite quickly. So we're looking at high speeds, but still small with respect to the speed of light. Let's read the question. So we've ignored the effect of rotation of the planets. Let's verify that this effect is negligible with respect to the gravitational field. Yeah, I guess I'm thinking now it's not stated very clearly. I should have said we've ignored the rotation of the planets on the clocks, and we're not going to take into account the effect on gravitation, but we're going to take into account the the movement of the clocks in our calculation. And we know from special relativity that moving clocks can measure different time intervals. There are clocks that move with respect to each other. So we need to know the rotation rate, and it would be fine if you said, or it'd be accurate enough if you said the Earth spins around 2 pi radians in 24 hours. But I just like to get people to realize that that's not right, because it forces us to think a little bit about our place in the solar system or in the universe. The Earth is yes, it's spinning around, and it's and in one day, in exactly 24 hours, we're again facing the sun. But it's but that's not the rotation rate of the Earth, because the Earth is going around the sun, right? So we have to take into account that the Earth goes around the sun, and well, but we know that rate, right? It goes around the sun once every year, and so in a 24-hour period, it's gone. It's gone 2 pi radians plus 1 over almost 365, right? Times 2 pi radians. So it's gone a little bit more. It had to turn a little bit more to face the sun again. So when you take that into account, the period of the Earth's rotation is less than 24 hours. No, of course, it's very small, but it's just it's interesting to take that into account, and it's not hard, and so I wanted you to think about that here. And I wanted to, I wrote out this question in detail the way I wanted you to think about it. I wanted you to, in other words, I told you, let's imagine we have 2 clocks, one in an airplane that's flying around the Earth, in such a way that it would be stationary in this Schwarzschild coordinate system. So it would have fixed phi coordinate, and that would demand that it flies at the rotation rate of the Earth, but in the opposite sense of the Earth. So it would have to fly from east to west, and then if it did so, such that its phi dot was this rate, then it would be stationary with respect to the fixed stars, but of course moving very quickly with respect to the surface of the Earth. And I put it in a low orbit so that we could say it essentially has the same gravitational field as the clock that's stationary on the Earth. Yeah, we're going to compare the clocks that are in the airplane with the one that's at this stationary on the Earth. And so we play this same game here as we did before, and we're going to measure the proper time interval measured by the clock. I said the one that's stationary in the Earth is in a laboratory, and the one that's in the airplane is in the avion. So A for airplane or avion, and L for laboratory. and we want to compare these two, and we use the same um, tricks that we've been using up till now, but now we have just one, just the Earth to deal with. Well, we're going to find it's negligible. So it's negligible on Earth and it's negligible on Mars. Mars spins at about the same rate as Earth. So we've already calculated the proper time interval of a clock in the airplane, because that's what we did actually in that calculation 11. We took a clock that was stationary, at the radius of in the Earth's gravitational field. So in the Schwarzschild space-time with mass of the Earth and radius of the Earth, but we ignored the phi dot. Well, that's what this airplane is doing. It's essentially holding still in the Schwarzschild space-time. So we have fixed radial coordinate at the radius of the Earth. It's in a low-flying orbit here, so that it's flying near the ground, and it was not practical, but just for argument's sake, its latitude, we'll keep it fixed at the equator to simplify the calculation, and phi is by construction is staying fixed. And so, but that's what we found before in equation 11. And now what we have to do is consider the clock that is in the laboratory, but now taking into account that it has a phi dot. And now we cannot use the formula, careful here, you cannot use the formula that we used earlier. Remember when we had a dt squared and a d phi squared in our calculation with Mars and Earth in orbit around the sun, we were able to I was able to write this as something in phi dot squared times d tau squared. You could do that here, but we can't. In fact, that's what I did to go from here to here. But we can't use that formula from the last tutorial. This one, you can't use that one that relates phi dot and t dot, because why? Because this is for following a geodesic. This is in particular circular geodesic or in Schwarzschild spacetime. But that's not what we have here. The clock in a laboratory is not following a geodesic. It's very important that we are straight on that point. We're not in a geodesic, but we can still, use the line element to find proper time intervals. I'm a bit lost now. Where are we? We were here, and then we replaced. Sorry, that was for the airplane, and this is the laboratory, and we replaced phi with phi dot. Yeah, and so we still use this line element to get the proper time interval, but we need another way of dealing with phi dot. Well, we know phi dot because that was given to us by the rate of rotation of the Earth. And at least we can't combine this term with this term, but we can just bring it onto the other side of the equal sign here, and then we have d tau laboratory. We can combine those terms, so we would have there's a 1 from this, and then that would be plus these coefficients. We're obviously taking into or factoring the d tau L squared and sorry, I've done several steps here at once. I brought that over here, and then I took the square root of both sides because I just had two terms once I factored here, and then divided that both sides by this term here, the thing that involved the phi dot over there. Sorry, I hope that was a lot to do in one step, but I think if you just sort of imagine you're trying to solve this equation, yeah, I think you can figure that one out. And now again, we have we want to take the ratio of this time, proper time measured by the laboratory clock and the airplane clock, and this term exactly cancels this term, including the coordinate time interval, and so you just have the ratio of these proper times given by this term here. And this looks, so we can say this is an angular velocity squared times a radius squared. This looks like a linear velocity squared. It's the linear velocity associated with the rotation of the Earth, which turns out to be 460, almost 65 meters per second. So this is the speed an airplane would have to go around the Earth in one day. So as I say, that is feasible, but it's supersonic. The speed of sound is 340 something meters per second. So this is a supersonic speed, but not unobtainable. And I'm totally unaware of what on earth I was doing when I called this 1.55 C. Yeah, so this is wrong. I don't know what I was doing there. I must have forgotten to put an exponent. All I can think of is that I forgot the exponent. In fact, I can look in the source file. No, it's not obvious how to fix that. I'm sorry, this is wrong. But this looks right. Well, we can guess about what this is. It's we want to compare that with the speed of light, which is 3 times 10 to the 8. And this is a little bit, this is about, yeah, actually it's about 1.5 times the speed of light, or 1.5 times 3, but times 10 to the 2. So it's 10 to the minus 6. Actually, yeah, so I think this is just simply 1.55 times 10 to the minus 6. Yeah, right. And then when you square that, you're going to get about 2.3 times 10 to the minus 12, right? And then you'd substitute that in here, and you get minus a half of that, which is yeah, well, I guess it'd have to be 2.4, and then well, anyways, I think this algebra is right because I do the algebra in Maple, and I just, the error is in I just forgot the exponent here, 10 to the minus 6. Yeah. Let me just verify that. Yeah, actually, let me, well, I have the Maple calculation in front, or I can bring it up, and I just don't want to mislead you in this, but the final result looks very reasonable. Yeah, that's it. It's just 1.549 something. So it's 1.55 times 10 to the minus 6. Yeah, I simply forgot the exponent in, so I'll put that in here now before I forget, times 10 to the, oops, minus 6. There we go. 10 to the minus 6. So you square that, you get something times 10 to the minus 12. Divide by minus 2, and you get minus 1.2 times 10 to the minus 12. So that would be less than half a millisecond in a decade. And so this is really quite negligible. So we finally got something that's not worth correcting our result for. And so we can have confidence in our previous results here. Remember, we can have confidence in this result that takes all the gravitational effects into account. We still have Mars spinning, but it's spinning even slower than the Earth, and it's or slightly slower. So it's these are not important effects. I want to wrap up by 5:15, so we still have a few minutes, but I can maybe make well, I'm happy to take any questions. If you have any questions or remarks, I can, it's tempting to, so feel free to interrupt me at any time, but if I don't hear anything from you, I'm going to maybe just make, since I have 10 minutes here, I'm going to make a remark on this equation here. This looks a lot like a factor of gamma, right? If you think about gamma from special relativity, it's 1 over the square root of 1 minus v squared over c squared. And here, I'm comparing a clock that is at the same gravitational potential in the Earth's gravitational field, but one's moving with respect to the other. So you might suspect that this is like gravity is just irrelevant here, and all I've got is clocks moving with respect to each other. And that's true. So why didn't I get a factor of gamma here? Precise why it's almost gamma, except the darn minus sign. Did I make a minus error? No, there's no error here. It was just a choice. It was a choice when I decided to describe the velocity as being the rate of change of the angular coordinate with respect to proper time. Think of the definition of phi dot. I think that's one of the very yeah, I decided to call this phi dot. I imagined that phi dot was the rate of change of this angular coordinate with respect to proper time, but within 1 part in 10 to the 12, that's the same as coordinate time, right? We've just decided that there is very, very little difference between coordinate time or proper time. So I could have said this is, partial or d phi dt, where t is the this coordinate time, Schwarzschild coordinate time. If we had done that, I'm going to write that down. Imagine I have, instead of phi dot, I have d phi dt, where if I'd use that as my angular velocity here, then I'm not going to do this calculation for you now, but I did it last weekend when I was dreaming this thing up, and I convinced myself that instead of the plus here, I would have simply had a minus, and then this would simply look like a special relativistic effect. It is a special relativistic effect. It's a factor of gamma, different. It's just that I chose to think of phi as being the derivative with respect to proper time, just because we had a phi dot earlier, which was the proper time derivative, and I didn't want to change things on you, but it would have been equally valid to have used the coordinate time derivative here, and then we would have had a factor of gamma. So this is just a special relativistic effect. And so even though we have clocks moving around in a gravitational field, we don't actually have to take into account gravity for this last question here. This question here, we're only taking into account the movement of the clocks at a constant gravitational potential. I guess that's my point. So I'm, yeah, that was easier to say than I thought. So that was worth it. But I'm done now. So if there aren't any questions, I'd like to stop there. I realize that you, so please say your question quickly if you have one. If not, I'm going to sign off. But of course, I recognize that questions might come to you, and almost certainly will, when you work through the control continue, which I hope is well. I hope you're well positioned now to attack that control continue, because it's a similar question. It's I hope a little bit more interesting question, because you've probably heard about the fact that you've probably I think you can see me now, right? Yeah. I think so. This hopefully is the control continue is a little bit more relevant to you, because we're not talking about clocks on Mars. We're talking about clocks on satellites that are in orbit around the Earth, the GPS ones. And so when you use your smartphone to tell you your GPS coordinates, for instance, say you're driving in your car, you use the phone as your Google what's it called, Google Maps to find your way. Your phone knows where you are by communicating with this GPS satellite. And that GPS satellite, I had to look up its altitude above the Earth, but once we have that altitude, we can figure out the gravitational time dilation associated with the orbit of those clocks. And it's not small. You're going to find what it is, and it's that has to be corrected for. So now um, if this ever comes up, a question at a party or something, is general relativity important in the solar system? It's a very small effect, but it's measurable and in fact crucial for the operation of your of Google Maps, or anything that depends on these satellite, GPS satellites. Okay. Well, have fun with that one. And I deliberately made a longer, more involved control this week, but I try to give you some extra help by having this TD today that is directly related to it. But once we get through that, it'll be downhill from there. You'll just have one more, and I've missed one, but I'm right. But I'm just going to give you full marks for that one as a little bonus, and because you've been all, or most of you have been quite good about doing these all year long. So I'm really happy about that, and I think it's really helped you absorb the material. So this, I would say this, so far this year has gone better than previous years. Not that it went badly in other years, but it's gone better this year, even better. And I think it's largely to your credit that you've followed through with these control continuities. So please keep up the effort. And that's all we. Yeah, we just this one, and then one more, which will be even shorter than the one this week. Okay, don't hesitate to send me questions. Same procedure as normal. This weekend I do not have kids, so I'll be even more responsive to questions. But yeah, let's say as a default, I'll check my email for your. I promise I'll check at noon on Saturday, and 6 o'clock, and again on Sunday. Yeah. Okay. Good luck with that. Thanks. Bye.